Writing and building secure software is a constantly evolving realm. With some solid knowledge of secure coding practices, you can help prepare yourself to be more nimble with regards to cybersecurity. Hi, I am a developer, architect, teacher, and perpetual student with over 30 years in development, much of that focused on security and security-adjacent topics. Join me in this course to help develop awareness on common security issues and security-focused processes. The goals of secure coding. Part of being a good developer is understanding what you need to learn and what you need to stay up to date on. So let's talk about how this course will prepare you for the day-to-day operations as a developer, keeping secure coding in mind. This course won't make you all knowledgeable about writing secure code. It's aimed at giving you the information you need and the support that you need to write more secure code. In fact, this is one of my primary goals for you. There is no way to say you are a truly secure developer. That's not completely possible. What I want you to take away is the ability to be called a security-minded developer. Another goal is to prepare you to be the champion for security practices on your team. What I've found in both my personal experiences around security and through discussions with others is that for a team to really embrace any sort of culture around security, you need a champion. Now, this champion can come from anywhere in the team, but in my opinion, the single most effective place for the champion is within the ranks of development. Forcing a culture on a team seldom works, and right or wrong, developers tend to listen to other developers more than anyone else on the team. This is why I believe the developer is the single most effective person on the team to lead this effort. They are listened to, and they can be the driver of grassroots change. The third goal that I have for you is to become a more effective voice in the software development lifecycle, or SDLC. This may sound strange at first, but if you work on a development team, you can only write a portion of the code. So while you may be great at writing code that is more secure, your personal impact on the overall code base is smaller than that of the whole team. In most teams, several developers are part of the code review or pull request process. So your impact can be dramatically increased by simply being engaged in code reviews from a security perspective. This also extends to other reviews in the SDLC like design reviews and requirement reviews. Now, if you're not a developer, you may wonder what value this course can have for you. First of all, if you're a development manager, you need to understand what your team is doing, what your team is spending time on, and what risks they're trying to resolve. If you're a project manager or Scrum leader, you also need to know why a development task may take longer because of security concerns. And if you're a quality assurance or quality control person for the team, you can leverage the knowledge of exploits and attack vectors to write more effective tests. And that's the ultimate challenge, realizing that security is a concern for everyone on the development team, and embracing it. Understand the attacker. The mind of an attacker or bad actor is foreign to many software developers. We spend our lives building things that we hope make the world a better place. Now, I know that this is kind of cliché, but the reality is most of us really want to write code that improves our business or engages our passion. As such, we are builders and makers. An attacker, however, has a very different mindset. Now, their motivations can be all over the place, and while it is important to understand these motivations, the simple fact is that they want to tear down what we build, and that's very hard for many developers to grasp. So, part of writing secure code is understanding the mindset of the attacker. The first component of understanding that mindset is looking at why they want to break your code. Now, The reasons can be as numerous as the stars in the sky, but each attacker has a motivation. Most attacks we hear about seem to be for financial reasons, but attacks happen for other reasons. Things like political motivations, revenge, or even building credit with other bad actors, to name just a few. I have seen attacks happen because people want to build a reputation as a security tester. Now, I'm not a fan of this type of extortion, but it may be a reason for attacking systems. Now, regardless of the why, it's very beneficial to figure out all of the possible attack reasons. This why is critical, because once you know why attackers might disrupt your application, you can start looking at the possible exploits that could exist in your system by applying their views and thought processes. This is really the heart of understanding the attacker. As a developer, truly understanding an attacker is one of the most difficult challenges in my opinion, but once you start recognizing their mindset, it opens up a wealth of new ways to protect your system. For instance, understanding their motivation allows you to look at an attack vector in your application by thinking through the lens of the attacker. Once you collect this information, you can start building an attack tree. The attack tree allows you to build scenarios based on probable attacks. With these scenarios, you can determine where you need to add testing, increase threat detection, or apply mitigating controls. Getting into the mindset of the attacker can be a huge undertaking, but it can reap significant rewards to your organization. Threat modeling. One of the best places to start your secure code journey is through threat modeling. Threat modeling is a process where you systematically evaluate your system design, deployment, and structure for potential attack vectors. This process is not only proactive, but also retrospective in nature, in that you constantly must evaluate new features and reevaluate existing features. Once attack vectors are determined, you use your threat models to build both mitigations and remediations into your system. Again, this is a retrospective process, where every mitigation can cause the threat model itself to change. This isn't a course on threat modeling itself, but I do want to at least call out the general steps and a couple of methodologies. System analysis is the breaking down of your system into its component architecture and understanding the data flows between your components. Threat identification is the evaluation of the attack vectors, methods, and motivations for exploiting the system. Risk assessment then takes a look at each of the threats and evaluates its likelihood, its impact, and the associated damage. Mitigation is the stage where we look at the ranked risks and strategically resolve, prevent, isolate, or build detection strategies for each of the risks. Now, there are a couple of common methodologies used for threat modeling, and many less common, but still effective strategies. The common methods include PASTA, or Process for Attack Simulation and Threat Analysis, and STRIDE, or Spoofing, Tampering, Repudiation, Information Disclosure, Denial of Service, Elevation of Privilege. My general thoughts on building out threat modeling as part of the secure coding paradigm is to start small and simple. This is a process that takes time, energy, and ultimately, experience to master. You'll see many packages, strategies, and techniques from various vendors. But in my experience, moving quickly and plunging in is not an effective strategy. Sure, you can do it, but if you do, be prepared to risk frustration, non-compliance, and general dissatisfaction with the process as a whole. The reality, in my opinion, is any work is better than none. So starting slow benefits your team even if you don't have a complete threat model. Understand your risks. One of the core tenets of security, especially in a software development shop, is understanding and mitigating your risks. An entire course could be devoted to risk management for software teams, but for this course, let's take a quick look at the basics. While I'd like to convince you that you should test every possible scenario on every release, the reality is this isn't possible in most businesses. There just isn't enough time in the day to write or execute every test. Even if you could write them all, execution then becomes an issue for most teams, as long build and development cycles are really an handy pattern in today's processes. To address this problem, focus on the high-risk areas and determine where to get the most reward. You'll see an immediate value from automating the mitigations and testing for these high-risk areas on each release. You'll have immediate feedback to your team and your stakeholders that the software you are delivering is not exposing you to these risks, or at the very least, not increasing your exposure. Understanding risks isn't only about testing them. If a software development team can identify the risks earlier in the process, more emphasis can be applied to requirements, design, and development to address them. In software development, we repeatedly learn that the cost savings of fixing issues earlier in the process is significant. While the team engages in understanding risks together, the awareness of these risks penetrates every job function. When you truly incorporate this model of identifying risks early in your development process, your entire team, your project, and your budget will benefit. Imagine for a moment you're a developer who understands the risk exposure of your application. You can then question requirements and evaluate design decisions that include these risks. More importantly, armed with knowledge of secure coding and risks, you can provide more tangible feedback on code reviews. Understanding your risk isn't static, however. Risk must constantly be evaluated and updated to match not only the changes in your functionality, but also the changes in the environment around you. Risk must constantly be evaluated and updated to match not only the changes in your functionality, but also the changes in the environment around you. Every day, new attacks are discovered, new reasons for being attacked develop, and new information is obtained. My suggestion is to leverage a portion of your regular planning sessions to discuss these new risks. Do it as a team and apply these changes to your risk register. Always keep in mind that the goal of secure coding is not just about the bytes, it's the overall culture that you're trying to create. One key area of benefit may be in the development of a risk register for your software. We'll talk more about this later, but maintaining a register like this helps with the identification, mitigations, and validation of those mitigations in your code. Understanding risks moves you closer to improving the security culture in your organization. Break what you build. As developers, our general strength lies in building systems. A huge part of the difficulty surrounding secure coding practices is that we're builders, not destroyers. That in order to be truly effective as a secure coder, we need to change our mindset a little bit. Developers interested in improving their security footprint need to develop the skill of breaking code. Now, I'm not going to argue that you should become an expert penetration tester. But there's real value in learning the basics of attacking systems. Now, some developers may want to go deep and learn how to write exploit attacks. If that's where your passion is, there's tons of value you can add to your organization. While this can be an amazing skill, the fact is that there are several really great tools on the market that allow you to attack your code without a lot of extended learning. The value of using these tools is that you can start looking at actual exploits in your code. By breaking your code, you gain many valuable insights into your application. You'll see how data is accessed and used. You'll see how logging output is generated and eventually consumed. It becomes a natural learning exercise that will increase your knowledge of the code base as a whole, not just the attack vectors. One of the biggest benefits of learning to break software is that you get to interact more with the security professionals in your org, or the security community as a whole. This is powerful when you consider how important collaboration is for a development team. Constructive collaboration with team members can never be discounted. And constructive collaboration with security teams can be even more valuable for today's development shops. The concept of DevSecOps really is about bringing security into your development processes, the same way that we brought operations into our development processes with DevOps. Everyone on the team learns and becomes responsible for the security footprint of the application. Once developers understand how to break software and start to have more constructive conversations with security professionals, the entire team will benefit. You'll hopefully see faster turnaround on bug fixes and better testing as the knowledge base grows on your team. Now, another benefit is the better you are at breaking software, the more prepared you are to fix your software when it does break. Or better yet, prevent security defects to begin with. The skill of breaking software can create a culture of secure coding. I encourage you as a developer to take time to learn the basics, and you will find amazing results in how you and your team approach security. Document what you understand. Documenting your designs, documenting your APIs, and documenting your code are all usually built into the team's development process. What often isn't part of the process is documenting all of the security decisions you have made. Now I know, I've heard all the excuses in the book about documentation. Heck, I've used many of them myself. I've heard documentation is dead the minute it's written, or documentation is never read, or that it's too hard to find the answers that you really need. The point is, however, that regardless of the excuses, there is value in documentation, especially in the security realm. One of the first things that you should document, even if only on post-it notes, is how you are going to deal with security-related bugs found in production. Now, I won't argue that you need a full-blown vulnerability management plan at this step. You definitely do eventually, but that's for another course. For now, you at least need to have a plan in place to prioritize and fix production security bugs, and then route them through your development process. This document can be very useful when a really bad bug or an industry scare shows its ugly head. You'll be better prepared to move the fix quickly to production and protect your company and your customers. You should also document your risks in a risk register. The purpose of this is to not only document the risks that are in the application, but the ways that you plan to mitigate those risks. This can be very valuable to a team when trying to determine where the risks are in your application during a planning session or a design review. Having them documented gives you the foundation when it's time to reevaluate your risks as well. I also believe in documenting your risk mitigation and testing strategy. This can be easily incorporated into your definition of done statement, assuming, of course, you want security testing to be part of that definition. I've gone as far as including risk testing in every release of the application by making these tests part of the regression suite. Now, there are a couple of other areas of documentation that are so important that they're worth mentioning here. One is documenting your security bugs. Now, this is beyond just production bugs that are usually tracked in an issue tracking system. This document should be in the form of a bug book, something I keep next to my keyboard every day. As you're either fixing or identifying an issue, no matter the phase, you should document it in your book. This bug book can then be reviewed at team meetings and used as training tools. Now be careful not to make this a blame game. Instead, make it an educational tool. You'll find that your developers can learn from each other's mistakes when you talk about them in a blameless way. The other area is documenting traceability between your automated tests and the risks that they address. Now, in my opinion, this documentation should be in the form of a common naming pattern for your tests themselves. One reason to do this is that as you evaluate your risks and make changes, you know immediately which tests you need to address, whether it's an update, a rewrite, or a flat-out removal from the test suite. Another is that this will help prevent regression of security bugs. This is why I actually believe we should incorporate the tests in our regression suites. These bugs can be especially nasty from a publicity perspective to have the same security issue identified multiple times. Now, this is just a glance of documentation, but I do hope it gives you a solid perspective into the needs of documenting your security stance and the value around it. Introduction to vulnerabilities. While we're going to be spending some significant time in this course looking at major classifications of vulnerabilities, I want to talk a bit about vulnerabilities as a whole, and some trends around secure coding. Let's start our conversation with the WOSAB Top 10. This may be the single most valuable resource for anyone involved in software development to start their learning journey. The Open Web Application Security Project, or WOSAP, publishes a list of the most common classes of security vulnerabilities every 3 years. Now, their focus is on web applications, but many of the concepts translate to other areas of software development, so there is value here for everyone. That being said, this view of security-related trends is helpful, but also a bit disturbing, because even though this list exists and is well known, the classes of vulnerabilities don't often fall off the list. As an industry, we know that SQL injection attacks are dangerous. We know how to mitigate them, but they keep showing up over and over again. This truth of our industry may be the single most important driving reason for building this course. We know the issues, yet don't have an industry-wide positive trend for removing them. As you dig into secure coding more, you'll find that the WOSAP Top 10 is a great tool, but not the most detailed or wide-ranging. The Common Weakness Enumeration, or KEY, is a community-driven register of security issues that have been identified. Normally, quests fall into the security operations process as we react to new vulnerabilities, but they do maintain a top 25 that mimic the WOSAP Top 10. Knowledge of these tools can help you stay on top of current trends of vulnerabilities in the wild. One of the biggest drivers of scheduling remediations is how you score your vulnerabilities. Now, I'm not going to go into the details for the various frameworks because they're outside the scope of this course, but ultimately, they all rely on scoring a vulnerability based on its potential impact and the likelihood of that impact happening. Various additional metrics can be added, but ultimately, you maintain a score of your vulnerabilities and then work them in ranked order. Keep in mind that your organization may prioritize fixing some of them based on customer concerns as well. So be open to the fact that you may not always work the most critical ones first. Your team should develop a vulnerability management process and leverage existing tools and frameworks to accelerate your journey. Input validation. One of the most repetitive security issue groupings we find in software development today is various input validation bugs. While input validation exists in many different contexts, we're going to focus on the client-server input validation issues and how to possibly address them. Let's get started by talking about the attack vectors at play. Injection attacks are one of the most common and most publicized exploits, not just in the input validation arena, but globally. Often when we think about injection attacks, we're talking about SQL injection, but there are several other types. In fact, any code that relies on an interpreter for execution can be subject to an injection attack. The concept is rather simple. A structured statement is created that anticipates user input to complete the statement before it is then run through an interpreter. For example, in SQL, we could write a statement that is something like select from users where username some value. Now at runtime, the software takes user input and simply concatenates the statement before execution. If an attacker can find this scenario, they can provide input that not only completes the statement, but also executes a new statement by simply adding a semicolon. This provides the attacker more information about the system than the developer ever intended. Scripting attacks are another very common vector based on lack of proper input validation. The most common and continually on the WOSAP top 10 is cross-site scripting or KESX attacks. The concept again is rather simple. The attacker injects a script through a user input field or some other post or put method. That script is then served to a victim through his or her browser, which is then rendered in the client browser, and the exploit is executed. Often these scripts send data back to the attacker server. What I've just described is called a persistent cross-site scripting attack. However, there are a couple others. Reflected cross-site scripting is often used in phishing attacks, where the malicious script actually originates in the request itself. There are also exploits in the document object model or DOM that can be triggered, but we won't go deeper than to just say that they exist. All of these exploits are based on lack of input validation. While these attacks can be nasty, the fixes for them are relatively straightforward. One approach is to require validation of all user input. One such validation technique is called deny listing. Deny lists look for key patterns like script tags to filter out the input. Deny listing is often one of the first attempts, but they tend to be easy to circumvent and should not be used alone. Another validation technique is called allow listing, which is much more effective than deny listing. Allow listing looks at the pattern that the data should have, such as length or symbols, and requires that the input matches that pattern before it's ever accepted. For instance, an email address must contain the symbol and end with a dot and a valid top-level domain. In either case, the validation should always be applied server-side and be the first thing executed. Now, you can apply validations client-side to save the server call, but it still must be executed server-side as well. It's important to note that some of these attack vectors can be mitigated in lower levels of the system, specifically SQL and associated injection attacks. More on that later, but it's a great time to discuss that security in layers is always the most effective approach. Communication channel. In a client-server architecture, there's always a risk of a security vulnerability existing in the communication channel between the two systems. Because of the way TSIP works, these communication channels are potential hotspots for attackers to exploit. The most common communication channel attack is the theft of sensitive information on the wire. An attacker who can gain access to the network of either the client or the server can potentially steal the information on that channel. Many businesses, for instance, provide free Wi-Fi, which is left open and unencrypted. This can become a source of theft, and your development team needs to proactively protect your customer. Much of this is accomplished by restricting access to unsecured Wi-Fi and the use of VNS-PS. When you have control of the network, however, the next step is enabling transport layer security, or TELS, on your channel. Through the use of TELS, you can ensure that the traffic in motion is encrypted. This reduces the risks of information theft over the channel, though it doesn't completely mitigate it due to potential man-in-the-middle type attacks. TELS is sometimes mistakenly referred to as SEAL, or Secure Sockets Layer. While they both serve as cryptographic protocols that provide authentication and encryption between the systems, SEAL has been deprecated and replaced with TELS. To set up TELS connections, a valid certificate is signed by a trusted certificate authority. Their certificate must then be installed on the server. Since the communication channel itself must be a secure one, it's always a good practice to redirect all traffic from TAPT to TAPS. Some may advocate for strict TAPS only, but remember that if your security makes your site unusable or frustrating in any way, it becomes ineffective, as ultimately you will lose users. It's also important that your certificates are valid, trusted, and not expired. Tools like OpenSeal make this validation easy. In addition, you can build up processes to manage your certificates on a regular basis. Now, when you control the actual code on the client side of the connection, you should always validate the certificate. This includes not only checking that it's valid, but that it has not expired or been revoked. Each language and framework has tools for making encrypted connections as well as these validations. Often developers skip that validation part, so make sure that you don't. The extra overhead is worth it because if a certificate becomes compromised, you have a way of protecting the client system from accepting a bad connection, which again can cause a leak of sensitive data. Using secure communication channels wherever possible will dramatically increase the overall security of your systems. Session management. Session management vulnerabilities are associated with web application-based client-server systems. Let's take a look at the vulnerabilities and mitigations in this context. To understand session management issues first, let's look at how TAPT works. TAPT at its core is a stateless protocol, which means there is no user data or other information stored between requests in the web server. In a pure stateless TAPT system, each and every request is independent of every other request, even if it's the same user with the same browser in the same general browsing session. Some developers feel the need to maintain some sort of state for the user, leading to the creation of the session. The session is usually initiated by some event on the website. Authentication is usually that event that starts the session and generates the unique token. The server shares that token with the client through a cookie. Now, every subsequent request from the client to the server will send that cookie and the token it contains. The server can then use the token in that cookie to look up the session state data. The vulnerability that can exploit this process is called session hijacking. This works by using the session's token, which is often created using random numbers. If the random number generator isn't secure, a bad actor can simply predict the value of the session identifier for a user. Once they can predict the pattern through an algorithm, they can generate a seed session and use it to grab the next user session. If you find yourself creating tokens for sessions, You must verify that you are using a secure random number generator. Most languages have a general random or pseudorandom number generator and a secure one. Always use the secure generator. Lack of communication channel protection can increase session management risks. If you don't mark the cookie to be secure, it may be passed over TAPT instead of TAPS. Another issue is when you create the session on the first visit, but don't create a new session when the user logs in. A session fixation attack can occur, as the pre-authenticated session token would now point to the authenticated session. Anyone who grabbed the session on plain TAPT traffic could use it once you log in, even though that communication is now over TAPS, with the secure flag now on the cookie between the real user and the server. Session creation isn't the only weak point, however. Session termination also exposes potential risks. A developer must ensure that when the user logs out, the session is invalidated. If not, the session token can still be stolen and used by a bad actor, even if the real user is no longer interacting with the system. Likewise, sessions should expire after some period of inactivity. If the user leaves the browser open but is no longer using the site, there is a risk of the token being stolen and used by someone else. In such cases, developers should provide timeouts for inactive sessions to protect the user. While this may frustrate a user to see the timeout, things are more secure when we destroy the session. Just be open to iterating on the timeout value to keep your users as happy as possible while driving towards security. Now let's be honest, very rarely do users actually log out of sites. Instead, they just close their browsers. Therefore, their sessions remain active and can be stolen. A developer should invalidate the session when the browser closes to ensure that the session cannot be stolen. Now, we don't always use sessions in web development, but when we do, we need to be aware of the risks. Protecting users in these situations isn't hard, but you have to think about the risks and make a global plan to address them. Error handling. Error handling is an important part of application development. It allows the developer to prevent the application from abnormal termination, while also providing a great place for troubleshooting breakpoints when issues do arise. But what makes it powerful for developers also makes it attractive for bad actors. One of the most frequent vulnerabilities comes from information disclosure through error messaging. In these vulnerabilities, the application raises an error that produces an error status. This error status usually results in a message like a 404 or a redirect in the web world. The vulnerability arises when that error message discloses information such as a stack trace or a database dump. This information can be very valuable for an attacker trying to gain entry into your system. Even the disclosure of your internal error codes can be used to attack you. How you raise an error can provide an attack vector as well. One of the most common issues that I've seen in applications of every type is in user authentication flows. Often developers will provide different error messages if the user doesn't exist versus if they entered the wrong password. This level of disclosure can provide a bad actor a brute force vector into your system because you are confirming that a user exists. All of these situations are very easy to prevent, however. We must first accept that error conditions will always exist. We need them to exist in our applications for flow control and to protect us from crashing. The fix isn't to prevent the errors, it's to accept them and make conscious decisions about what information we display. In our invalid login case or a password reset case, the developer should only disclose that the situation exists, not which case we're in. The language should be consistent so a valid user can take appropriate action, but a bad actor won't be given too much information. It takes some time to get good at using consistent language, but often it's just a matter of taking the time to document those messages. Review the text and make sure that errors don't disclose internal system information. In the former case, trapping the error and returning a generic error page usually allows you to provide logging in the trap while displaying a generic error state to your users, again, preventing leaking of information. Code reviews and documentation can help a bunch in these cases. But an even better model is to actually test your error states. When you do so, you can provide guidance through the test about what text should be displayed and what shouldn't be. All too often, developers focus only on the positive cases in their tests, and that leads to issues like information disclosure. So I highly recommend testing positive, negative, and error states. This can also be a great exercise to ensure your error messages are consistent, valuable, and don't disclose sensitive information. Logging and output. We've discussed issues with disclosure through error handling. And in a similar vein, it's possible to expose too much information in our log messages and our system output. We will start with log information because it's much easier to inadvertently cause issues in how you write log messages. There are two classes of vulnerability in log messaging. The first is to expose too much of your internal workings, and the second is to expose too much information about your user. When you write log messages, often you are providing detailed information about what's actually happening in your system. This data can be critical when an issue arises, whether they're security-focused or operational in nature. The log messages can also provide too much information, making your log aggregations an attack point. Events are one of the things you should always log, whether they're user events or system events, such as authentication or task completions. You should also always log errors, especially in controls that are designed to prevent attacks against your system, such as input or output validation errors. Session events are also a great place to provide detailed logging, specifically on creation, reanimation, or destruction. In addition, you need general application flow in your logs for operations. While these things should appear in your log messages, there are several things that should never appear. Credentials and connection strings for backend services like databases should never be logged. Tokens for sessions or specific events likewise have no place in your logs. Encryption operations and keys as well as user passwords also fall into this category. Sensitive personal information like email addresses shouldn't be in your logs unless this information can be useful in troubleshooting. But if it must be in the logs, it should never be in plain text. Instead, it should be hashed using a secure cryptographic hash, and then that hash is what should be put into your log message. That way you could recreate the hash for troubleshooting, but not the reverse. If the information has no value in troubleshooting, it shouldn't be in your logs. One useful strategy for logging is to provide a set of methods that write to the logs instead of directly calling the logging APIs. This allows you to provide proper uniformity and sanitation of the log data to protect the system and the users, all while promoting good security as well as operational behavior. Application output also needs to be inspected. System output should be validated, just like user input, to ensure that you are not creating risk to other systems that may be downstream. Data should be filtered and sanitized so that the user sees what they need to, but not so much that an attacker could use it as an exploit. Since many systems are used by both users and other systems, the output can expose other vulnerabilities and should be treated as something to be protected. These vulnerabilities really come down to disclosing enough information to help you do your job, but not so much that you become the attack point. It's a fine line, but one that a collaborating team can solve universally. Internal data management. There are often many secret values or secure data points that an application needs to operate successfully. These data points can be as simple as URLs or as complex as encryption keys. While this data is needed for applications to operate in the wrong hands, they can be treacherous to a system. Let's start our discussion with a common use case, connecting to a remote service. Usually, to connect to a remote service, you need to store the URL of that service, along with credentials or tokens needed to consume that service. That information is needed by your application at runtime. Serving that data at runtime can be the challenge, and we'll get to that. But first, let's talk about the attack. The attack vector associated with this should be relatively straightforward. If you expose the data that you need for your system to operate, the attacker can then use that same data to mimic you to your backend service, giving them potentially unrestricted access. They can steal data, modify data, or just simply delete it, causing various levels of chaos to you and your users. Solving these problems is relatively straightforward. We just have to keep in mind the risks. One way to help solve these issues is through a secret storage service. Your system will need a way to authenticate to the service, so you still need to protect that data point. However, you can set most of them up so that the user never needs to be involved. Once set up and wired in, you can get your application the data it needs to operate at startup or runtime. These tools are powerful for your application because many of them create a way to not only create, but also rotate your credentials. Another key takeaway to prevent vulnerabilities related to data management is to ensure developers never commit sensitive information to source control. Even non-prod systems can provide an attack vector into your application or your system as a whole, so no sensitive information should ever be checked into the software configuration management or SCAN. You also need to protect who has access to data points, as well as the systems that store them. Unauthorized access to the running application can either directly or indirectly cause a leak of these sensitive credentials. Unauthorized access to the running application can either directly or indirectly cause a leak of these sensitive credentials. Again, we find that much like other vulnerabilities, these can be mitigated with a little bit of common sense, but we have to understand that the issue exists to begin with. Configuration. A common theme should be identifiable by this point. In many cases, the processes that make running, deploying, or troubleshooting an application much easier can also be used to exploit an application. Configuration of our application is another such case that builds in our previous topic of internal data management. So let's start by explaining what configuration is. To the SANS Institute, for instance, secure configurations apply to the systems and servers. It's the software and operating systems running on the machines. It's definitely critical to keep systems patched, but from a development perspective, this isn't the configuration we are talking about. When I talk about securing your configuration, I'm referring to the feature flags, options, and other data elements that your application needs to run, often served to the runtime during startup. Many times as developers, we want a soft rollout of features through the use of feature flags or to provide ways to put the application into a higher state of logging. Inherently, these features are not bad on their own. However, they can expose your system. For instance, if you're developing a feature and you want to roll it out to beta testers that you trust, you may put feature flags in place. Your beta testers will have the documentation on how to turn that feature on, but you acknowledge then that you may still have bugs. Now, if these bugs expose the system to attack, compromise, or some other vulnerability, you have now exposed that application. Likewise, if you expose backing service URLs through configuration, they can be modified by the user, or worse, an attacker. They can trick the application into exposing information by simply changing the URL. Mitigating these attacks is actually relatively easy. First off, consider packaging beta versions of your software separately, and then deliver that to the trusted beta testers directly. This will reduce the risk of feature flags exposing software that isn't ready for prime time. Also, be careful about what functionality you expose through configuration. If the configuration exposes where sensitive information or application information goes, or how it is even exposed, reconsider how that configuration is set. If an attacker can identify how to modify the level, type, or location of this information, they can use it to expose details of your system or your users. Consider the case of data in the database as a way to store preferences. In a thick application where the database is embedded or on a local file system, preferences of this type act as raw configuration flags. Attackers can manipulate this data to expose an attack vector into your application stack. One final place to consider configuration is in your runtime itself. For instance, if you're using an application server to run your application, its default configuration will most likely expose too much information about your application. You should apply best practices from organizations like WhatsApp when configuring your runtime to prevent information disclosure that could be used to attack your application. Once again, it comes down to common sense. Only expose options you need to expose. Don't rely on configuration for handling sensitive data or processes. Protect your internal processes, especially the sensitive ones. Database. We talked about a couple of the potential issues with databases from other perspectives, but databases and other backing services are used in multiple ways for targeted attacks. Let's start our discussion once again with SQL injection attacks. I mentioned these attacks when we discussed user input validation, and indeed that is a good mitigation for these attacks. Another good mitigation is using frameworks or strategies to connect to databases. SQL statements should include bind variables and parameters. Now you can write full statements or use bind variables. Creating full statements is susceptible to injection attacks because these statements are often concatenated with user input strings like in our previous example, but when you use bind variables and parameters, you remove that risk because of how the drivers will create the statement for you and escape any text. Using a bind variable allows you to place a variable in the statement where you expect the user input to be added. For instance, select from users where username bind variable. Then we will execute that statement by passing a parameter for a bind variable from the validated user input. This strategy dramatically reduces any risk of injection attacks. Databases have other issues as well, and one goes back to secure communication channels. Often database connection strings are performed using plain text communication channels. If you own the database client code, its runtime, the network, the database management system, and all of the hardware involved, you may be tempted to think you are at risk. We must, however, consider that all too often the internal user is the most dangerous attacker in a company. The proper way to connect to database systems is through secured channels. Most, if not all, databases allow for encrypted communication between the client and the server. Yes, There's more configuration for both the database administrator and the developer, but not having a way for someone to sniff the traffic on the line, it's worth it. Databases also often contain sensitive information. Encryption in transit is only part of the solution. You must encrypt your data at rest as well. There are many ways to do this, but I actually prefer a separate encryption routine from the database itself. In the model I use, the encryption key is served to the application and the encryption is done there. At this point, any attack on the database requires another attack on the application or the encryption key holder. You also need to encrypt the disks as well. Layers of security are always the best bet. Databases are valuable to developers for many clear reasons, and as such, they are great targets for attackers. Consider this when you interact with databases and apply some best practices. File and I/O. The file system can be a dangerous place for applications, and bad actors love to leverage it to find exploits. Attacks on the file system can be relatively easy to exploit, so it's a great arena for new attackers. Furthermore, the results can be devastating to the systems involved. As we look at the risk management profile, the ease of attack in conjunction with the damage potential indicates a clear need to take these seriously. Now there are several areas we need to focus on with the file system as well as file input and output. The first we will discuss is often more infrastructure focused, but in a DevOps world, that line is very blurred. You need to ensure your application is run in a user process that is controlled. You should only provide access to the file system to that user that the application needs in order to run. This is often considered in server-side applications, especially in the Linux world, but the same cannot be said for desktop or mobile applications. While sandboxing environments help, the fact is that the developer still needs to allow the application to read and write from a finite location on the file system, and the process needs to have that same access. When an application needs to read from the file system, consider using read-only files in these cases. Attackers love to modify files that applications need to operate in an attempt to exploit the application. By leveraging read-only files or media, the attacker has less opportunity for attack. Another important attack vector is file upload. When a system allows file uploads, it becomes an easy way to impact the system as a whole. The first scenario is a system that parses a file that the user uploads. An attacker can inject malicious data that forces data leakage, unexpected operations, or simply causes crashes, making the system unavailable. The mitigation for this attack is one that we've discussed: input validation. The system shouldn't trust the data in the file without first inspecting it for malicious behavior based on how the data is consumed. Another scenario is infected file upload. While this generally is an infrastructure concern, developers need to be aware of the scenario in order to engage the proper infrastructure teams. In this attack, we start with a system that allows file upload, so the attacker then embeds some form of malware into that upload. The mitigation starts by providing a sandbox area for intermediate uploads. The upload process should write the file and then trigger a malware scan. Once that file is determined to be clean, another process can move it to its final location, and so our theme continues. Never trust what your user provides. You provide as much isolation as you can, and never provide more trust than is absolutely necessary. Memory management. Memory management vulnerabilities are a very special class in that they're only exposed in certain languages and certain situations. The most common, and the one that I'll focus on, is the buffer overflow attack. I want to start by providing a clear indication of how bad buffer overflow vulnerabilities are. There are several yearly contests that result in large sums of prize money for security researchers that compromise systems, often called rooting. Some of the most profitable vulnerabilities are a result of buffer overflow attacks, including many of the 0 days that are found. These attacks are catastrophic and can be expensive. But unfortunately, they can be hard for those developers who deal with higher-level languages to see or even understand. In higher-level languages, for instance, we seldom deal with raw memory allocations. Even in languages like Go, Java, and C where we have pointers, we're not usually able to manipulate raw memory without dropping into unsafe code. As such, these languages are usually safe from these errors, but there are lessons to be learned from those of us that use these higher-level languages. So I encourage you to listen and find parallels in how you deal with data structures in your code. In lower-level languages like C, for instance, you're dealing with memory allocation and pointers to that memory. As such, you're now fully responsible for checking the bounds of the variable, and here enters the problem. I want to give you a simple example that, while made up, still shows the point. So let's say you declare two variables. The first is a character array of, say, 10 bytes, and the second is an unsigned integer of, say, 4 bytes. They happen to be next to each other in memory. Now, you have a program that asks for input and stores that value into that first array. You expect no more than 9 characters in your response. However, you don't check the length of the input. You just read it to the variable. If an attacker writes a value that is, say, 13 characters in size, it will overwrite the 4 bytes of the integer with the last one being a stop byte. If your program then accesses the unsigned integer and the attacker has done his or her homework, the program may execute other instruction sets, often at the command of the attacker, through user input or exception flows. Some exploitations can impact the stack, others can impact the heap, but both can be leveraged in specific cases, and neither of them is pretty. There are a couple of mitigations that you can put in place, but really there's only one fix. One of the mitigations is to randomize your memory allocations so that the likelihood of memory spaces touching is decreased, but this is nowhere near perfect. The same can be said for various protections for pointers, executable space, or stack alteration. Again, while these protection strategies can be good mitigations for legacy code, it's not foolproof. The best way to protect against these attacks is actually a threefold approach. First, use native protections in your development language. In addition, you should validate your inputs to ensure they are within the acceptable bounds and they cannot overflow the buffer. Finally, leverage a good testing strategy. One thing you should note is that even if you aren't writing code in assembly, C, and Fortran, you may be leveraging components that are. You need to consider this whenever you write code, that input and boundary checks are always important, and ignoring them can lead to security vulnerabilities. Dependencies. Dependency management is often the bane of software engineering. When it comes to security-related topics, it's even more so of a problem. Many times when we write software, we could write the most secure code ever and still be susceptible to security vulnerabilities because of a dependency. We all know the stories of the old and vulnerable component that caused the system its data, or worse, all the customer data to be exposed. Some of these leaks have been so bad that they put a large portion of the population at risk for either credit fraud or identity theft. This is something we must always remember when writing software and trying to secure it. So obviously, the exploit is out of our control since we don't own the code. Now, if it's an unpatched defect, we can of course fix it ourselves, assuming it's an open source component. However, that still is a process. The reality is, however, that many of the vulnerabilities have already been discovered. These discoveries are documented, and often they indicate the dependency's version number that is impacted by the security issue. They also often document when the issue was fixed. As such, the simplest path then is to upgrade your components to a fixed version. Now, I don't want to pretend that this is easy from a system level, but as for fixing issues with dependencies, it often resolves the issue. We're going to assume for the sake of this discussion that nothing new is introduced, which of course is not always the case. The real question, however, is not how to fix these, but instead how to identify them. There are actually several tools, some open source, that run scans on your bill of materials or your dependency graph, and identify which of your dependencies are actually vulnerable to an attack. Some paid tools even have detailed analysis that provides more information about the attack possibilities, but ultimately, they all point to similar or identical databases of COIs and VIS. So your strategy needs to simply be this: stay on top of your dependencies, look for problem spots, and address those problems as needed. Physical security. So far, we haven't mentioned physical security. The reality is that it exists in all facets of security. That being said, when working in embedded devices, you've already lost the battle for physical security by default. In my opinion, this is one of the hardest aspects of secure coding in the embedded space. Simply because you cannot maintain physical security. Consider the case of building an embedded component for a car. Now you can do everything possible to secure the device. But the communications bus from the car may have a problem. Your lack of control of the ancillary systems allows your system's data to be manipulated or stolen. So now let's take a closer look at the device itself. Every port and every exposed plug is a potential attack vector. You have to control all the input and output on that port, and any flaw there can expose the system itself. But even not having exposed ports isn't safe enough. If they can get access to the circuits themselves, they can harvest insights and data that may provide for data leakage. Now, let's take this a step further. The attacker starts with one device and finds a weakness. They now can exploit every device you have released. The bad actor can use this to steal data, cause risk to life and vehicle attacks, or use your devices as a lawn packs for other attacks. So how do you mitigate this? The answer is through layers and layers of best practices. The hardware engineers must have security in mind during design. The software engineers must have security in mind when developing. Then you bring your product to the security team and let them break your devices. This cycle exists, no matter the development environment: attack, break, mitigate, and repeat. Side channel. In the embedded world, the side channel attack can be very frustrating, to say the least. In a side channel attack, we start with the fact that devices during normal function leak information about their operation. Things like power consumption, timers, radiation, and even acoustical signals all tell a story about the device. So let's talk about a couple of the common attacks. The first is looking at power consumption to provide insights into the data being processed. Another is reading the electromagnetic radiation emitting from the device to determine how it operates. Yet another is looking at the timing of actions performed to gain insight into the algorithms being used. All of these can be leveraged for negative purposes. So now let's talk about a few of the possible mitigations. One is to leverage constantly timed algorithms. These are algorithms that take the same amount of time to execute regardless of the input values. Timing attacks are of no value when the algorithms are all constantly timed because there is no variation. Another is the concept of obfuscating the secret values in the system. By randomly masking or obfuscating the secrets, it is harder to leverage power analysis or timing analysis type attacks to harvest information. In addition, adding things like electromagnetic shielding or components designed to securely perform sensitive operations can reduce the risk of side-channel attacks. Of course, both of these add significantly to the cost per unit. As with most things in security, layers of protection are often the best defense against these side-channel attacks. Memory. Like we have previously talked about with memory management attacks, the embedded world deals with all the same problems, the difference being in the constraints. Embedded systems are often severely restricted in memory as well as processing power, and these restrictions impose a greater risk of memory-based attacks. We've already talked about buffer overflow attacks, and these still apply to embedded systems. I want to discuss a couple more here that are more embedded device focused. The first is code corruption type attacks. An attacker will attempt to overwrite the code instructions in memory, usually causing malicious code to execute, which of course can cause the machine to be cracked or compromised. Another type attacks the control flow of the system itself. When code is written to protect itself in embedded devices, the wrapper to that protection can be attacked. This wrapper, as I call it, controls the flow, and as such, can be exploited. The control is thus redirected to attack the underlying software itself. Now there isn't a lot new here in terms of mitigation, as we still need to sanitize our inputs and properly allocate and delegate memory. What is different is the compounding effect of the embedded device itself. Lack of physical security control, lack of full control of the side channel, coupled with smaller memory and processing, makes this concept of memory management significantly harder with embedded devices. If you're doing low-level or embedded development, you have to constantly keep these in your mind. By being aware, following best practices, and applying layers of security, you will reduce your risks. Software versioning. When we have an embedded device, the software will eventually need to be updated. This brings us to our software versioning attacks in the embedded world. In this attack, a bad actor will leverage a flaw in the firmware update process to carry out their attack. Let's start out with the granddaddy of this attack vector, at least in my opinion. It is labeled as a time of check, time of use attack. In this attack, the bad actor utilizes the firmware update process to inject malicious firmware after the update process was validated, but before it was written. Another attack impacts those that leverage digital signatures for validation. Often in embedded devices, the capacity for key size for asymmetric encryptions is small. This opens up a greater possibility that the signature can be cracked. They may not even have to go that far if they can bypass the check. In either case, they leverage this to provide malicious firmware to the updater. Now, there are others, but the idea behind these attacks should all be pretty clear. So now how do we mitigate these attacks? The first is to build a more secure firmware updating process and harden it so that the risk of the attack is less. This cycle of improvement and hardening will help build out a more secure system. Another important consideration is forcing software updates. Since you have no control over the device itself, You need to provide a mechanism for routine updates, preferably without user involvement. These routine updates will give you an opportunity to patch the system and remove risks of exposed vulnerabilities. Finally, as with the hardening I mentioned, attack your device often. By constantly attempting new attacks, you can improve the chances of finding an issue before an attacker does, giving you a chance to patch it. Layers of mitigation and testing is still the best option for protecting our systems, along with a healthy dose of humility. If you assume your system is never secure because it isn't, you will maintain a more healthy view of your security posture. Third-party components. As with all software, the dependencies and their potential vulnerabilities and bugs are a topic to deal with. In the embedded world, you also have to think about the components themselves. Let's start with the software dependencies. Like we talked about before, software dependencies can be a source of vulnerabilities in and of themselves. As such, you have a need to evaluate risks and update your software as appropriate. Of course, just like we talked about with firmware, we have to deal with the fact that we have to get the users to update their devices. The best strategy here, especially in the age of connected devices, is to force an update to the software, just like with the firmware. This gives you an opportunity to keep your software updated without user involvement. If user involvement is a must, you need to find a way to convince your users to upgrade their devices regularly and prevent the reversion to impacted versions by not allowing it to be downloaded or used. Some companies even invalidate the signature of old versions as soon as the new version is released and validated for some time. Now, let's talk about the hardware side. Of course, those third-party components may have software that needs to be patched with the aforementioned process, but what about the hardware components themselves? If the third-party component causes your system to be at risk, you have to protect your system from itself, so to speak. You may find yourself writing code in an update to bypass or sandbox the at-risk component because you are stuck with it. You cannot just simply swap it out like you can with a software component. Maintaining a solid bill of materials, or BOM, along with detailed entries for software components, can help you stay on top of this attack vector. But ultimately, there's only so much you can do. You don't own the device any longer. To sum up, keep your software patched, force users to take the updates, and be sure you monitor your BOM for potential hardware flaws that need to be patched in future software updates. Never assume that because the device is released with no known security issues, that it will always be that way. This will potentially change once the device is in the wild. Authentication and password. Authentication is not an easy operation when it comes to modern software. On paper, it looks very straightforward. A user comes to your site, enters their username and password, and clicks Submit. You then evaluate the username and password and determine if this is indeed the correct person, and go from there. Simple, right? Well, not so fast. Authentication itself has many security implications that lead to attack vectors. One such attack is an enumeration attack, which we have already discussed. If you provide separate messages when a wrong password is entered versus when an unknown user enters your system, you are telling an attacker if they have the username for some user in your system or not. So the key here is to keep the messaging consistent. Another issue to address is the actual time it takes to perform authentication. This is a case where faster is not better. We're going to talk about cryptographic algorithms in a bit, but know that some hashing algorithms are slower than others. And when it comes to authentication, slow is not a bad thing. Now, when I say slow, we're talking about hundreds of milliseconds slower, not seconds or minutes. The reason for this is because the faster the algorithm is, it gives the attacker more operations per unit of time to brute force a password. So the key here is to use a good password hashing algorithm that was designed for authentication. Another issue that just makes the previous do worse is simply allowing brute force attacks. If you do not provide a maximum number of bad password attempts before you institute a lockout procedure, you're setting your site up to be attacked. Not only will this put your customer data at risk, but you will also be allowing more load on your system than you even should be. The key here is having a maximum number of incorrect attempts and storing those failed attempts in a database. Storing this data in a session is not sufficient. I also want to point out a couple of other issues really quickly, because in all honesty, we could go on for days. Never ever store your customer's password encrypted, or worse yet in plain text. You have zero reason to know or be able to identify a customer's password. If you can do so, an attacker can as well if they gain access to your system. So only hash passwords. Also, leverage short-lived unique links for password resets. Password reset functionality should provide unique tokens to customers through their verified email address. You should never provide them a password in plain text email. You should also never allow anyone from your company to manipulate a user password or impersonate the customer. Also, like before, consider how you respond to password changes on screen. If you know the user, is the message the same or different than if you don't know them? A final point that I want to bring up about authentication and passwords is to consider the complexity. You would be better served to only use lowercase letters in a password of sufficient size than to have a short password with complex rules. The first is easier for a user to memorize, while the latter is next to impossible. Now, I'm not going to argue that special characters and uppercase letters add to the search space, but I will state that an all lowercase 29-character dictionary word-based password would currently take over 1 trillion years to crack randomly. An 8-character password with symbols, numbers, and mixed case can take minutes to brute force attack. Authentication issues can arise if you don't take this topic seriously, which, believe it or not, can be the case. I urge you to really think about authentication and passwords the next time you interact with that part of your system. Authorization and access control. Providing authentication for an application is only half the battle. You also need to provide the rules around what that person can access. This is called authorization, and faulty authorization can lead to security defects that often are hard to track down. Let's start with the basics of what issues exist around authorization. Often defects arise in this arena because we have access control lists in place, but they are not applied correctly, or they simply have not been applied at all. In either case, a user could get access to resources or data that he or she shouldn't have access to. Consider the use case where your site has a user portion and an administrator portion. If you don't have solid access control lists, your users could potentially access your admin section of your site. This obviously gives them more control than they should ever have. Now take it a step further and consider that in your admin site, you can see all the demographic and personal details of your customers. Imagine not only the negative publicity your application would receive, but also that your customers could potentially have their identity stolen, and your site would be responsible. A couple of rules to consider when doing authorization. First off, you should always do authorization checks server-side in a client-server program, and never solely client-side only. If an attacker spoofs the client side and you don't check rules server side, you'll potentially expose protected transactions. In addition, all permission state changes should require logging out and then logging back in. Even your privileged users should have access in place and not be able to change them in a single session. Sometimes for troubleshooting and support, an impersonation model is put in place, despite this being a generally bad practice. If you must do impersonation, it should only be part of authentication, and the session should be static when it comes to permission models to help protect from internal threats. It is advisable to have detailed logging of every event during an impersonation session. Furthermore, each transaction should check the authorization of the user. It should not simply be checked once. This becomes even more critical in a microservices-based architecture where the systems themselves are distributed. You should only serve data or execute a transaction if the user in scope, which we call a principal, has the authority to do so. So mitigations for these risks are twofold. First and foremost, you need good controls in place around how you review and control access itself within your application. Using code reviews, design reviews, and even acceptance criteria can help you evaluate authorization during development. This will not only help you prevent issues, but it will also help you understand the authorization flows that do exist. In addition to reviewing code, you should focus on documenting and discussing changes to access control lists on a regular basis. The second mitigation, and maybe even more effective, is good testing of your access on every build. You should leverage role-based users in your test suites and look at every transaction from both a positive and the negative perspective for every role. Essentially, you're building a matrix to check all your access controls. Spend some time in processes and testing to help prevent these security risks from becoming an issue for you. Cryptography. Cryptography is a very hard subject for most developers. Thankfully, those developers that do understand cryptography are very good at it, making things easier for the rest of us, assuming we follow the rules correctly. So let's start by talking about the security risks associated with cryptography. First and most common is the use of broken cryptographic algorithms. Now, the term broken is a little overloaded here. When I say broken, most often, it means that the algorithm has been cracked, theoretically can be cracked, or has a flaw that has been identified. Many developers implement an algorithm for encryption, hashing, or digital signatures that they have used before, but it may no longer be considered safe. The mitigation for these flaws is quite simple. Use the latest and greatest algorithms that serve the current and possibly future needs. Now, you don't need to be bleeding edge, but you do need to use algorithms that are not yet cracked, and I do mean not cracked yet. There is always a risk that the cracking will be possible in the future for any algorithm. So you need to keep tabs on the algorithms that you use and their acceptance by the industry. Ultimately, upgrading is going to be needed. One thing to note closely associated here is choosing the wrong algorithm. Say you need to hash passwords, you could use SHA-2 from a pure crypto perspective. However, it's too fast of an algorithm and opens you up for brute force attacks. Instead, consider something like bcrypt. Ensure you are using the right algorithm for the right use case. The second security risk is that there is a case where developers misuse or misunderstand the algorithms that they are using. Things like initialization vectors, salt, knots, and other parameters have valid places in certain crypto algorithms, and they should not be ignored. In addition, Often key sizes can fall into this arena because insufficient key size can ruin a great algorithm. This can lead to cases where the algorithms are no longer as safe as they should be because the implementation wasn't correct. The mitigation for these flaws is to ensure you are using the algorithms correctly. If you don't know if that's the case, just ask. I have yet to meet a developer who knows everything. It's perfectly okay and honestly advisable to be a little humble and ask questions. Misusing algorithms can be as dangerous as not using them at all. Of course, there's a little exaggeration there, but opening yourself up to a rainbow attack because you don't understand salt is a pretty bad flaw that could be solved with a simple question. One issue that honestly bothers me is poorly implemented crypto algorithms. There are some developers that feel that they know crypto well enough to implement the algorithms more efficiently. Now, I won't say that they fail more often than not, but leading crypto and security researchers usually argue that they do. The possibility of a closed homegrown implementation. Having a flaw is usually too great for most companies to accept. The mitigation for this is quite simply never roll your own crypto. I call this the first rule of Crypto Club because in my mind, this is a no-brainer. I feel like I have a good grasp on crypto, and I would never in a million years roll my own for a customer or an employer. There are good libraries out there that you can use. In short, properly use a well-tested algorithm that hasn't been cracked and ask lots of questions along the way. As you have seen at this point, the general themes for all of these mitigations should be clear. Layers and layers of mitigating controls, constant self-attack and testing, followed by focused hardening. This pattern will help you build a more secure system. Requirements. One of the first places to improve the software development lifecycle, or SDLC, regarding secure coding is in the requirements phase. We usually spend a lot of time determining what the customer wants, how they want to use it, and what the rules are around that use. We don't, however, spend a lot of time evaluating the threats introduced because of these new features. So let's start there. Starting with threat modeling in the requirements phase of the SDLC starts to not only detail risks, but allows you to modify your requirements to reduce those risks. Software is constantly changing, but it's always cheaper to fix the issue, no matter the issue, the earlier you can in the process. Along the same lines is addressing the risk register. You need to keep the risks up to date and ensure that the new risks are documented. Through this documentation, you are providing information to development and CA that they can leverage to improve the security of the system as a whole. When building requirements for a system, knowledge of common vulnerabilities can help you create both functional and non-functional requirements to address the potential for a vulnerability. By being involved in requirements, you can call out potential vulnerabilities to help ensure they are not forgotten along the way. If you leverage acceptance criteria as part of your requirement process, you can call out these potential mitigations as acceptance criteria themselves. All in all, security must be kept in mind by the whole team, but it starts with the requirements and the review of those requirements. This isn't just a task for the creator, the reviewers must be fully invested as well. Design. As we continue talking about culture changes around secure coding in the SDLC, I think it's only fitting to spend some time around the point where most developers begin their engagement, the design. Now, technically I'm talking about two distinct phases in one, those being the architecture and the design. Many, however, ignore the distinction and simply call it design. So to avoid confusion, I'm going to do the same. Now I generally start with solid architecture characteristics and the associated styles that accentuate the characteristics that I care about most. In this phase, I believe it is important to not only look at what style fits best, but look at the attack vectors on that style. This matrix of risk and reward will help you pick the best style when there are multiple ones in consideration. You may even find that a hybrid approach mitigates the risk the best. So it's not always an all-or-nothing answer. Now at this point, we generally get into system design. We are looking at how we will leverage the architecture to design our system as a whole. In these design routines, we build diagrams, and those diagrams can be a big help. As you design your system, you're exposing where the attack vectors can be. We're looking for connections and edges that can be a potential attack. This is where we want to build in mitigations. We shouldn't stop here, however, because when we get into the component design, we have to look at more isolated attacks. Making design decisions here often involves documenting your mitigations at the code or even algorithm level. The output of the design phase, or phases, depending on your organization, should include risks identified at every level, as well as specific mitigations that need to be in place at the system or code level. Now I suggest getting deeper into the details of those mitigations with both technology and code than you normally do in the rest of your design. Development. In this course, there's been a large focus on the development side of secure coding, but I want to emphasize a little about how you can leverage this knowledge to positively impact your company culture. First and foremost in my mind is education. If you have seen any of my other courses or heard me speak, you should get a feeling that I'm all in on education. This course may be the start for you in secure coding and security in general, but please don't make it the last. You have to start living this stuff at least a little in order to really grasp the full reality of it. Follow blogs and X accounts, because that is how you'll hear of the new attacks that you may need to react to. If you hear of a vulnerability in a component you use the day it's announced, you'll have the information and more time to fix this issue before it becomes a problem for you, assuming of course that you weren't hit before the announcement. You also need to test your own skills. We talked about this earlier in the course. Try and execute a few attacks every now and then. Practice reading buggy code and practice fixing it. These skills not only make you better at security, they also make you better at pure code reviews. You also need to be the change agent for your team. Development is hard, we all know that. Security is even harder, but a champion will help the team more than any mandate pushed down from above. You may inspire others to start down the path with you. Remember, one of the most important things for a security-minded developer is a healthy dose of humility. This is a super important aspect of working in security, and one that I personally struggled with a lot, at least at first. Most of my strong opinions about development were actually formed out of mistakes I've made, and those in the security realm are no different. I've messed up cryptography, data security, and written code that's susceptible to vulnerabilities because I thought I knew better. It took me realizing the humility is a better approach, and that allowed me to get past the causes of these early mistakes. You won't know everything there is to know. You will definitely make mistakes, just own it. It will make you a better developer, a better secure developer, and honestly, a better person. The most important aspect, however, is to apply this knowledge often. Look at code reviews from the security mindset. Look at development tasks and designs and try to break them. Look at risks and ensure that they are properly mitigated. Question behavior that seems to put your company or your customers at risk. Ultimately be the champion. Testing. In my mind, no single aspect of the steal can have as much impact as testing. But also no single aspect of the steal is ignored as much as testing. Testing for security is no exception. In fact, it may even be worse. There are 3 key strategies to testing for security. The first strategy is to leverage attack trees. As a team, you will design user personas and attack trees that give you step-by-step attack vectors against your application. You can then weigh the likelihood of these attacks and the risks presented by them. Once you have this information, you are given an ordered list of scenarios that should be mitigated. You then write tests to confirm that the mitigations are in place. This testing is highly effective in ensuring that your controls are in place correctly to help protect your system. These tests, if properly automated, can then be run on every build and every release. Now, keep in mind attack trees do change over time, so your scenarios and tests will also have to change. The next strategy is to leverage the risk register. As a team, you should maintain a list of risks within your system. These risks will also have controls and mitigations in place. Some of these risks should be security-focused, and this is where testing comes into play. Your risk register should be leveraged in testing to ensure that your risks are handled appropriately. As such, your security risks should also be tested on each and every release. Once again, risks change, and you have to address these changes in your existing tests, as well as your new tests. Another area that testing comes into play is with penetration testing tools. You may not have a security-focused person on your team who can do this, so you may have to take the lead. Penetration testing tools often require an initial learning curve to use effectively, and then another, sometimes steeper learning curve, to understand and interpret the results. This testing, however, can become essential to making your software more secure by identifying vulnerabilities. Some tools can even plug into your SICK pipeline and self-discover your system based on your other tests or service documentation. Now, these tools can be expensive, but are very powerful. You shouldn't try to tackle all of these tests at once, however. Make a testing plan that works on one area and try to make significant headway in that area before moving on to others. Now, a word of caution here. While you may be tempted to start with penetration testing, keep in mind the security mindset of the whole team. If you dump a list of vulnerabilities on them day one, they may never catch up. Instead, work together and focus on your testing strategy. Deployment. Deployment of code is one of the areas that gets ignored all too often when it comes to developing a secure coding plan. This is an unfortunate oversight, as there are many ways to improve the security of your system at this point. One of the weakest points of secure deployments is how you manage the sensitive configuration of the components being deployed. The use of files on the file system or in startup scripts all too often count as secure enough, when in reality they fail. They expose significant attack vectors into your systems or the systems you depend on. There are, however, very powerful tools and patterns that can be leveraged to improve the secrecy and security of these sensitive data points. Some of the tooling has sophisticated APIs and startup routines that ensure your system will get its config and no one else can. If you're deploying to a containerized framework, you also likely have built-in support for secrets, so at least consider using those. Another step that seems to increase security is automation. Anytime a human has to be involved in deployments, you increase the risks of compromise. The operator may make a mistake with permissions or leave something open that shouldn't be. Worst case scenario, the operator may get disgruntled and become the bad actor themselves. While automation is by no means a complete stopgap, it can be a great opportunity to prevent internal attacks. By forcing code through a peer review cycle and then only deploying through an automated gated process, you can ensure that the code running in production has been fully vetted. As long as the boxes doing the deployments themselves are secured, you have set yourself up to be more secure than not. There are several other aspects of secure deployment strategies, but that can be a course on its own. My purpose here is to get you thinking of ways to improve your culture of security, especially around deployments. As always, try to think like a bad actor and use the insights gained from that thought process to focus your efforts around preventing attacks. Operations. Operation workflows can be very tricky because many times engagement from an operations perspective comes during an incident. When your system is in a degraded performance state, the last thing we worry about is security because we want to get our customer back up as quickly as possible. But you still have to think about security in your operation activities, usually before the first incident. Let's start with the access needed in an incident. All too often, our developers need full unfettered access to quickly resolve an issue. This, of course, isn't what we really want, but there are a few options to do this in a more secure way. One of the best options I have seen is a permission elevation tool. A developer has standard access, but during an incident, he or she can request elevation of permissions. Many of these tools require linking to the incident management tool to ensure the request is valid. Once the request is processed, temporary elevated access is granted, and all actions are logged. This is a powerful way of controlling access while allowing your team to get a customer backup because it records, protects, and ultimately expires access. Another beneficial process during an incident that also helps with change control and root cause analysis is the logging of every action taken down to the keystroke. During an incident, it helps to have a person designated to take notes of everything done. As long as the execution is in the open, you can come back after the incident and close any gaps in security mitigations that you may have open during the resolution. Something else to think about is how you inject log and metric data. Finding the right balance between enough information to troubleshoot, but not so much as to risk a data leak is difficult. A strategy that I often employ is through my runbooks. Instead of feeding the information to my log aggregator or metrics collector, I simply document scripts or commands in the runbook to harvest the data. This layer of obfuscation gives us what we need, but does so in a less risky fashion. Don't ignore your operational needs, but don't ignore the risks either. Take the time before the first incident to set this in motion. Containerizing concerns. If you're working with containers, I want to take a brief pause to talk about the security concerns here because they impact almost every phase of the SDLC. A secure product lifecycle is important in general, but with containers, it is critical. Many times, we start with a published base image and just use it. For smaller companies, this may be fine, but I encourage you to start working on your own base image and build everything off of it. This has a couple of benefits. 1. It allows you to control what is in every image, since every image starts with your base image. The second benefit comes from the dreaded 0 day. If the OS you built your base image off of is compromised, you can simply patch it once, and it will cascade out to your application images. The next area of focus is on the images themselves. Relying on a base image is great, but you can add a lot to a base image. I would encourage you to quickly stop doing that. You should only be adding the bare minimum that you need when building an image. That goes for your source code as well. Many times, we leverage builders in our images to provide an intermediate image that we compile on, and then a final image that is much thinner and devoid of the source code. The operations phase of the stack has implications as well, especially in a container orchestration flow. Your images should be built very thin, so the number of debugging tools that you have available is reduced. Often we have to manipulate the OS of the image during runtime to find issues, but we have to remember to get rid of that image when we're done. I also will often deploy temporary images to my environment with all of my debugging tools, and then remove it when I'm done. Images have a lot of benefits in the world today, but if you are using them, consider the potential risks you may have to deal with and go from there. Best practices. Security is often a moving target. When you are starting down this path of secure coding and ultimately a culture of security, it's easy to get lost. I'm going to suggest you focus on the most current best practices. Consider development tasks like source control, unit testing, static and dynamic code analysis, and peer reviews as best practices to help secure your system. Don't be afraid to attack them one at a time and get processes in place that work for you. You don't, however, need to recreate the wheel. There are several great resources on the web for free that will help you build a platform of secure development. I've added some of them to the resources article at the end of this course. Requirements and design are no different. A lot of time and effort has been put into developing secure practices around these tasks. Again, many of them are published for free. Consider risk management as one of the bigger areas here, and focus on how the industry is managing risks and documenting them. While not everything will work for you, you may find enough to get you started and ultimately save you some valuable time. One area I would highly suggest you follow industry standards around is vulnerability management. Many people have put in a lot of time into developing standards and strategies for companies and teams to manage their vulnerabilities. Things like scoring, ranking, and prioritizing vulnerabilities have been solved as well as ways to accept those risks. Tracking and reporting on vulnerabilities has also been vetted pretty well in the industry. As always, you will make parts of it your own, but definitely use what you can. Finally, when it comes to testing and deployment, there is a lot documented, but you will have to work through a significant amount of it on your own. Start with the basics and reach out to the community. A lot of work around penetration testing and automated deployments has been solved, but things like attack trees are not as common. You may prioritize your individual workloads based on what is done and what isn't. Ultimately, I want to encourage you to start somewhere. Try out what your peers are doing and go from there. Next steps. Before we talk about next steps, let's do a quick review of what we've discussed. We started off with an overview of security, as well as risks. We jumped into attacks that impact web and client-server programming, thick applications, as well as embedded systems. We also talked about cryptographic attacks that span all system types. From there, we discussed the stealth phases and how we can impact our security program as a whole. So what's next? Well, there are a lot of ways to go. You can focus in on your area and learn everything there is to know, be it Kafka embedded systems or designed for SaaS applications on the web. You can also choose to focus more broadly and look at the realm as a whole. You can choose to develop ethical hacking skills to improve your development skills, or even provide that function to your employer. Essentially, the sky is the limit as to where you can take this. Just don't stop. This is a topic whose importance cannot be undersold. I want to end by saying thank you